And my background is a bit different. I come from the geometric algorithms and applied topology, topological data analysis community. So all the talks are really interesting to me. It's fascinating. And what I want to talk about is reconstructing a kind of a skeleton structure, a hidden structure from data, in particular a geometric graph structure behind data. And probably the approach that I'm going to take is a bit different from what I've been hearing so far, but hopefully give you a different perspective as well. All right, so I guess I don't have to really motivate the importance of graph as the object that we see in different kind of data analysis applications. They can be the hidden space where the data sampled from could be graph-like. Could be a geometric graph-like, or it can also be more like this is the simulation of the dark matter and the filament structure. It can also be abstract graph, and the graph arguably is one of the simplest nonlinear, non-manifold structure behind the data. Okay, so I have been interested in looking at different questions related to graphs and the metrics on graph for a while. And the particular question is that how to recover a graph structure from data under different setting. I emphasize the different setting here because it depends on your input, the type of input, naturally, the approaches would differ and the theoretical guarantee would also differ. Okay, in general, when we design the algorithm, we hope also to provide certain theoretical guarantee. And as you'll see later, the model is also a bit different from what we have seen today. Okay, so let's say if you have points sampled from a hidden space around a curve. Okay, so there's this classical concept called principal curve that one can try to model, and then there's also algorithm developed to compute this hidden curve. Okay, and there's been a line of work extending this also to more general objects, including graphs. Although in general it's quite challenging to model it for graphs. Now, if I assume that the points sample from a hidden graph, not just a curve now. And suppose I put a stronger condition on the points. I assume that the points are coming from very near, close to the graph, namely within something called house of distance, bounded house of distance to the hidden graph. Okay. For this kind of setup, I can use something called the read graph to help me to extract the hidden structure, and there are certain theoretical guarantees that one can provide for that, okay, for the specific setting. The read graph is a global structure, so the advantage of this is that it tends to be able to identify the junction points more reliably, which is in general challenging when you have singular manifold type of structure. Okay. Now, that was this setup. But what about we also have background noise? When you have ambient noise, the points can be anywhere. Okay, this becomes more challenging, that how to recover the hidden graph structure, and that's what I want to address in this talk. And in particular, I'm going to give you a framework which is based on something called discrete Morse theory, plus persistent homology, which is one of the important development in the field of topological data analysis in the past 20 years. Okay, and I'm going to start with a motivating example of road network reconstruction, and I'll move on to the algorithm, and then also at the end give you the theoretical guarantee that we can provide for the approach. Okay. All right. So let's say here's a real problem. I have a bunch of trajectories that users, any driver with your mobile phone can provide. Okay, so this is the city of Berlin, and from these trajectories, one hope to reconstruct the road network behind automatically. Okay, now, so, or further, it doesn't have to be trajectory data. I could just give you satellite images, and I say that reconstruct the road network. Okay, and so the problem is important. It is useful. You can see that the applications of this, and there has been a lot of interest in the GIS community on this problem. But it's also challenging because, for one thing, when the user provides trajectory, they don't care about where they're providing. So you have a very non-uniform sampling of the hidden road network. Okay, so it's rather non-homogeneous. And also, the trajectory can be very noisy. So this is from the taxi data of Beijing. So you really don't see where the roads are, but they are there. Okay. Now, a lot of the work to recover this hidden structure very often is based on local information. We locally decide, you can use any mechanism, try to decide whether this is, what's the likelihood that this is on the road, off the road, and so on. But very often this decision is made by using local information. Okay? And many approaches using explicit threshold, which is challenging when you have a very non-uniform sampling data. As this example shows here, this is actually the density field of the road. You have major highway where the sampling is much higher compared to the little roads next to it. Okay, so the thresholding, there would not be any threshold that fits all. Okay, even locally. Okay, because I mean at the intersection of the small road and the major road, even locally cannot just use a single threshold. Okay. So as I said, the framework I'm going to use here is that I'm going to use the discrete Morse theory plus the persistence. So discrete Morse theory, as you'll see, is that help me kind of give me a way to handle the structure. Okay, try to get this global structure, and the persistence help me to handle the question of noise. Okay, now because it's using something which is a global topological structure behind data, it's more robust to the noise. And even when you have gaps in your data, but since the decision is made in the global manner, you tend to just go through that gap. Okay, we'll see some examples later. Okay, all right. The main idea is very simple. So here's the idea. So you give me the trajectory data in the specific application. Okay. Let me first just convert that to a density field. So in this case, we just sample the trajectory and did a kernel density estimator to get a density field. In this case, your density field is the scalar function defined on R2, okay? But this methodology works and when the domain is high dimensional or manifold, doesn't have to be Euclidean space as well, okay? Okay, so now I can view this density function, look at the graph of this function. This gives me a terrain in this case, R2, okay? The sampling could be non-uniform, but still, around, even though that I don't really see where the roads are, but close to the road, you can imagine that the sampling should still be higher, the density should still be higher than off the road. So this is not a critical point because it may not be higher than neighboring points on the road, but it's kind of higher than things going off the road. Okay, so when I do this, this will probably give you the image of that. What we're looking at where the roads are is like the mountain ridge of this density field. Okay, so naturally we say that, okay, how about we use the mountain road as our roads, okay? And this mountain ridge, we're going to use the so-called one stable manifold of this function to capture this mountain road, okay? The mountain ridge, sorry. Okay, let me first. Many of you probably knows some basics from the Morse theory. So imagine that I give you a very nicely behaved function on a D manifold, in this case on R2, okay? And the gradient of the function is just you look for the steepest descending direction of the function value at any point x, okay? And the critical points, this is just showing the gradient at x is going, so here I'm taking the negative of the standard definition, that's why I'm always going downwards, okay? And the critical points are basically where the gradient vanishes, okay? These are the red and yellow and the green dots on in the picture. Okay. Now, if I imagine that if I drop a drop of water on this terrain, then the water would flow following the gradient direction, right? This traced out by the water drop is called something called the integral line. Okay, that's what I'm drawing over there. Okay, the integral line passing through x. Okay, you can also go inverse direction. Suppose your water always flow upwards, then it can also go upwards. Okay, now in the end, because if the gradient, this kind of integral line always ends at the critical points, because that's where your gradient vanishes. There's nowhere to flow. That's where you stop. Okay, and I'm going to look at some specific type of integral line. I'm going to look at the integral line going from maximum to the saddle. So in this case, you see the saddle S over there, and let's say the maximum, the two maximum M2 and M1 going to the saddle. Okay, in general, for high-dimensional data, this is a so-called one-stable manifold of the saddle point. In the high-dimensional case, you would look at the one-stable manifold ends at d-1 index saddles. Okay, so now intuitively, you can think that this is where, in general, when I drop a drop of water, it will flow to the basin, to the minimum. Okay, but they don't always. If I drop a drop of water here, it goes to this basin. But if I go a little bit off to the other side, it would go to the other side's basin, right? In the middle, there's some separation. That's your mountain ridge. Okay, this middle one is the one stable manifold to the saddle. Okay, it's like the mountain ridge from max to saddle around the basin. Okay, so I want to use this to capture the mountain ridges and then use that to get the hidden road. Or in general, the hidden graph structure from your density field. Okay, this is just another picture to show that along this one stable manifold, locally, if you look at the density field, kind of cut across orthogonal to your this mountain ridge, you're going down on both sides is critical. Okay, but not necessarily on this green one. This is a real example of the from some density field. Okay, now. This sounds intuitive, okay, sounds very good, but this is the intuition from the smooth theory when we have the, we have a nice Morse function on a nice domain, okay. In practice, what we have is that we have some triangulation of the domain, and the function is usually just given, we can estimate it at, say, vertices of this triangulation, okay. So what do we do in this case? Now I can take a piecewise linear approximation point of view. I can try to approximate the gradient at every point, just do the same, and then try to approximate under the PL setting, what does it mean to have this one stable manifold? Okay, I can do that. And there are early work on this. Now, for one thing, this is rather unstable numerically speaking. Okay, you are looking at some differential structure. Okay, also, later, as I said, I also want to handle noise. I would like to be able to simplify this. Okay, when you talk about simplification, it becomes harder to do this very numerical approach. In two-dimensional case, it's still handleable, but going above, beyond 2 dimensions becomes much harder. Okay, so what we're going to do is actually using this Foreman's discrete Morse theory, which essentially is a combinatorial version of Morse theory. I'm going to introduce some of the key concepts in a moment, okay? But the main advantage is that because of this combinatorial nature, you'll see that I don't really need to handle numerical estimation so much, okay? And one important thing is that later this one, when combined with the persistent homology, would also be able to effectively help me to simplify the computed one stable manifold. So instead of talking about discrete Morse function, let me just go directly to the discrete Morse gradient vector field. Okay, just because essentially gradient vector function, they're kind of equivalent up to. Okay, so if I give you a simplicial complex, it's just a triangulation, a nice, in this case, just 2-dimensional triangulation, namely edges, vertices, and triangles. Okay. A discrete vector, a gradient vector, is actually now a pairing between 2 simplices. Okay, it's between either vertex, edge, triangle, or edge or triangle tetrahedron. In other words, between 2 simplices, that one is the face of the other, where their dimensions differ by only 1. Okay, I'm showing some example here. So this edge is paired with this triangle, and this vertex is paired with this edge, and so on. Okay, so we see that this is just a combinatorial pairing. It's a matching between simplices that have the face-coface relation. Okay, and if you have a collection of such pairing, and nobody ever appear in more than one such pairing, then we call this a discrete. We call it a Morse pairing. Okay, you can think that this is almost a discrete vector field. Okay, and if a simplex never appear in any pairing at all. What does it mean? This pairing you can think is the flow, is the gradient vector, okay? If a simplex didn't appear in any pairing, then it's critical because it's not going anywhere, okay? So the simplexes that not paired at all is called critical. So in this example, this triangle, shaded triangle here is critical. There should also be vertices. This round dot, if you can see at all, they exist. I can prove that. So they are also critical. Okay, so they don't appear in any pairing because this flow doesn't go anywhere there. Okay. So I need one more notation, which is actually it's easier here. A so-called vector path essentially is trying to mimic the flow path that I mentioned earlier. This is basically a sequence of either vertex edge, following the gradient pair, and then go to one other vertex of this edge, and then follow another gradient pair, and so on, alternating between the vertices and edges, or alternating between edge and the triangle, where it's either an edge is paired with a triangle, and then you go to another edge of the triangle, and then continue. Okay, so this is just kind of mimicking the flow integral line that we mentioned earlier. Okay, so this is called a V-path. Now, if a V-path is acyclic, namely it doesn't come back to the self, then it's gradient path. Because gradient field, you don't come back to yourself. It's not an arbitrary vector field. Okay? And if you have an entire discrete gradient vectors, a bunch of pairings between simplexes, such that there's no cycles, then that's a valid discrete gradient vector field. Okay? So it's a very combinatorial view of the gradient field that we see earlier. Okay? Now, I didn't talk about what is a discrete Morse function, but in some sense, this discrete gradient vector kind of also, if you have that, then there exists a discrete Morse function, which I didn't introduce, corresponds to it. Okay, so it's not important here. And there are interesting relations between them. You can view, for example, you can view that in the smooth case, if you have a so-called index k critical points, like a minima is the index 0 critical point. Okay, so if you have index k critical point, then in the discrete case, you can roughly think that you are going to have a critical simplex of dimension k. Okay, this is a weak correspondence, only true in certain cases, but it helps you to think about this discrete setting, the combinatorial setting. Okay. As I said earlier, that we are interested in the one stable manifold. Okay, for a two-dimensional domain, when you have a triangulation on two-dimensional case, that's basically supposed to go from maxima to saddle and then go to maximum. Okay, that means you're going to have triangle edge pair. Okay, and in high-dimensional case, if it's d-dimensional case, you're going to have dimension d simplex, dimension d minus 1, dimension d minus 1. Okay, which is actually much harder to maintain and also simplify later. So what I'm going to do is that I'm now going to invert my function, my density field. I'm going to actually think that I want to get something called one unstable manifold, from minima to saddle to minima to saddle. The nice thing of this is that now this, in the discrete case, it corresponds to vertex edge pair. Okay, this also means that later, when I need to compute it, I only need the subcomplex of your input domain of dimension up to 2. In other words, your domain can be d-dimensional, but I only need the vertices, edges, and triangles, because I'm going to only looking for this one unstable manifold, which is vertex edge path. Okay? All right. Now, as I said, one of the really nice things about discrete Morse is that it provides you this very simple combinatorial way of simplify it. Okay? By this I mean that to cancel out critical simplexes. When you cancel out the critical simplexes, you also reduce the number of, because now if an edge is not critical anymore, you no longer have one unstable manifold going into it. Okay, so it also reduced that, so you simplify this, one unstable manifold. Okay, what is the cancellation operation? Now, suppose in this case, use E1, and in this case, all the red ones are critical. Okay, so let's say that I have E2 and V2 are critical. I didn't draw all the gradient vectors. Now between E2 and V2, there's a unique path between them. Okay? If there's a unique path between two critical simplices, to cancel both of them, what you do is that you simply invert the direction. Okay? Now this red V2 was not paired with anybody, but now I make this V2 pair with this edge, and then the next vertex pair with the next edge, and so on. And this would render both V2 and E2 not critical anymore afterwards. Okay? So you're reducing the critical simplices. And we do need the condition that to cancel a critical pair of simplices, you have to have only one path between them. Because if you have two paths between them, after your cancellation, you form a cycle. Okay? Because after cancellation, one of this paths, let's say we cancel the left path from T to S, after cancellation, all the arrows get inverted, then you got a cycle going back to T. Okay, so that's then the cancellation is not valid. So this is originally also introduced and described by Foreman, and as long as there is a unique path between them, then you can perform this discrete this cancellation operation. Okay. All right. So you may say that so far all good. You talk about some combinatorial pairing, and then you can also have a way to simplify them. But what does this even have anything to do with our density field to start with? There's no function value in some sense anymore. Okay? And also, the cancellation I just said, it just said any critical pair of critical simplices, as long as there's a unique path of this V path between them, I can cancel. And there are many, many choices. There's no canonical choice who I'm going to cancel. Okay, so in general, how should I do this cancellation? Okay, so if we have a density field at vertices of our triangulation to start with, we would hope that when I cancel critical pairs, I should try to preserve the important real feature of your hidden density field and cancel out the small ones. Okay, and I want something to help me to guide me to do this cancellation. Okay, and for this, I'm going to introduce this so-called persistent homology to do that. Okay, so the persistent homology, as I said, is one of the important developments in the past 2 decades. What I'm going to just to give you some idea, what I'm going to show you here is a really very simple toy version, not showing the full power of the persistent homology, but hopefully this gives you some idea of what's happening here. Okay? So let's say that, suppose I give you a function, in this case a very simple real valued function defined on R. Okay? The domain is very simple in this case, just a line. Okay? And I want to characterize this function. Okay? Now, we see critical points of this function. They kind of indicate important mountains. But to see how important those mountain peaks are, I cannot just use the function value, right? Because, for example, I have function value of similar function value or high, but that one, arguably, there's only one important mountain peak over there instead of 2. So the function value itself doesn't really help me to indicate the importance of it. Okay. So now what I'm going to do is that let's imagine that I'm going to sweep the domain. This is the graph of my function, but I'm going to sweep the domain increasing function value, and I'm going to keep track of what's happening to the sublevel set, things below it. In general, I'm going to keep track of all the homological feature, but since this function is so simple, I only need to look at the 0th dimensional feature, which is just connect components information. Okay? So at the beginning, I have 2 components, and when I pass through, and this just means that I'm going to look at connect components information, ignore the homology. When I pass through a local minima, what happens is that a new component is going to create once I pass through this. Okay? So something's happening here. A feature is created. Okay? I pass through another minima, another component is created, and x3, another component is created. When I pass through x4, what happens is that 2 components in my sublevel set now get merged. Okay, in other words, some feature got killed now. Okay, and I'm going to, in this particular case, I say that's the one created, the x3 got killed. It looks reasonable, and there's actually a mathematical way to decide why that's the case. Okay, but this two, you can think of the one created at x3 now got merged into the bigger one component. Okay, and I continue. So this 2x2 will be paired with x5. The component created at x2 will be merged to other bigger ones at x5. And in the end, these are all the pairing that you're going to get. Okay, so what this convert is that you give me a function, but now I basically give you a bunch of pairing between kind of critical points, and this pairing makes sense in the lifetime of each feature is basically the function value difference between the pairing. Okay, so you can think that the function value difference for each pair, this gives you the importance of this feature. Like x3, x4 is a very small feature, but x2, x5 is a much bigger one, and x1 and that one is a much bigger one, and so on. Okay, so this lifetime gives you the importance. Okay, so this critical points got paired up in a meaningful manner, and their importance is kind of captured by this lifetime. So I'm going to use this intuition it turned out that in the discrete setting, this is in the smooth setting. In the discrete setting, you have a arbitrary simplicial complex with some function value given at vertices. Then you can do the piecewise linear extension of that function, and then you can compute the persistence that I just described. Okay, there's an algorithm called persistence algorithm that can do that. Okay. The output of this algorithm would pair up all simplices, and the pairing, the function value difference between the two simplices will give you the importance of those features. Okay. All right. I hope this gives you some idea. But the algorithm, now we're ready actually to talk about put the algorithm together. The algorithm is very simple. There's only 3 stages. You give me this triangulation with function value at vertices. Okay. The first stage, I'm going to compute this, run the persistence algorithm, and compute the pairing of the simplices. Okay. Again, what happens is that this pairing captures those features that we just saw, and their persistence give you the importance of them. Okay. The small ones are considered not important. Okay. Now, for the discrete gradient vector field, I'm going to leave a lot of the work to the persistence algorithm. I start with something called a trivial discrete gradient vector field, where everyone is critical. Okay, so everyone at the beginning is critical. Okay, then I'm going to use the persistence to help me I'm going to find all the critical pairs who's using the persistence, the output of the persistence algorithm. Okay, all of those pairs whose persistence value is smaller than a threshold, say delta, I'm just going to do this cancellation process and cancel it out. Okay, that's the second stage. Okay, so you start with something where everyone's critical, but as you do the cancellation process, there are fewer and fewer number of critical simplices. Okay, and in the end, I look at all the remaining critical edges. Why critical edges? Because those are corresponding to the saddles. Okay, then I trace their unstable manifold in this discrete gradient vector field to the minima and output it as my graph. That's it. Okay. Okay. As I said, the algorithm works for any d-dimensional domain, and you don't need a triangulation of the entire d-dimensional domain. You only need up to the 2-dimensional simplices inside. Okay. Okay. So this is just an example. The blue ones are trajectories, and the dark roads are the output, and what you don't see underlying, I hope you can see the ground truth, the real roadmap. There are many things we don't capture because it's not captured in the trajectories. Okay, so this is just to show the effect of the persistent simplification. This is from Berlin. If you use a very small threshold, you see that you get a lot of roads, true or real or not real, but as you increase the threshold, you have fewer and fewer important roads left. Okay. This is just to show that the thresholding would not work because you cannot find with a large threshold, the downtown area is completely covered, and with small threshold, you miss a lot of information. Okay, and now this is just to point out that this is before our work. This is state of the art. This is our result. You see, the main advantage is that because we're using this global structure, you see the previous approaches tend to have these segmented pieces because it's hard to understand the global connection. But now you're using the mountain ridge, this backbone of your density function, to force you to connect them up. Okay. Okay, so let me actually quickly move on. This is just to show that we actually combine this with, if you're given satellite image with some training data, we can actually first train what could be the potential road, and then use this approach and get the reconstructed road from satellite image directly. Okay. We also use the for neuron reconstruction. Okay. Let me just use the remaining couple minutes to tell you that some of the guarantees that we can have. Let me skip this part. Number one is that I should point out that on the surface, it's like that I'm putting two different things together. Okay, a priori, it's not even clear why they match. Why should I get something meaningful? Okay, so that was our starting point, that it sounds reasonable to put them together, but why should they work? Do they really work? Can you really prove something? So one thing that we observe is that so this step, as I said, requires that I find the critical pair of critical simplices that not important. Then I have to revert the gradient paths between them to simplify it. Okay. What we observe is that since we are interested in only this one-dimensional structure ultimately, okay, this one unstable manifold information, turns out that I actually don't have to do that at all. I can actually first compute a certain spanning forest. Okay. Once I have that spanning forest, I have all the necessary information that I need to recover the one unstable manifold later. And then when the last stage, I simply then collect the correct paths. I never need to maintain any discrete gradient vector field at all, even though that the whole premises, the whole intuition comes from that. Okay, this also makes the algorithm extremely simple and clean. Okay, we have on the GitHub, and you're welcome to apply it to your data. This is just the point that I'm saying there. And the second thing is that, so here is a simple noise model. This is not a noise model that I'm proud of, but it's a first step. Suppose you have a true graph in the d-dimensional domain there that you want to recover. Okay, now you give me a density field. Okay, let's assume that the density field satisfies the following condition. Imagine that there exists some small neighborhood of your true graph. The small neighborhood, I call it G omega. This is the yellow region in this picture. Okay, and assume the small neighborhood has the property that this neighborhood itself deformation retract to the hidden graph. Okay, kind of you can collapse that into the hidden true graph itself. Okay, and my density is that. Intuitively, my density is that within that small neighborhood, I'm much higher than outside that small neighborhood. Our motivation of generating this density model, other than that this is something we can prove guarantee, is that you imagine that first your density is actually really cool. Namely, within the neighborhood, it's 1, outside it's 0. Okay, then you add small noise everywhere, white noise everywhere. Okay, that's basically, this is the model. So under this condition, okay, then you can prove that this is the geometric closeness, namely the graph that you reconstruct will lie, number one, within this G omega neighborhood. So if omega is small, that's the width of your neighborhood, that means geometrically you're close to the ground truth. Okay, so now note this does not say anything about smoothness of your reconstruction. It just says geometric house of closeness. Okay, number two, we can also talk about that you also, topologically speaking, you're having the same topology from this. Your reconstruction is a homotopy equivalent to the ground truth. Okay, if this is in d dimension, in 2 dimension you can get something even stronger, which is that your small neighborhood actually deformation retract to your reconstruction as well. Okay, that's this. The last one is only for 2D. Okay, all right. I think I put some slides for the sketch of the idea of the proof, but I think I'll just ignore that. Okay, now, as I said, this is not the best noise model, okay? But from a theoretical point of view, actually, just when we started, it's not even clear. Even if I give you points sampled exactly on the graph, does this procedure where you put two things together give it back to you? Okay, even that wasn't clear. So this is really one step to go towards that, okay? The other thing that really give us hope is that in practice, I mean, this input clearly does not satisfy the noise model that I just described because it's very non-uniform. Okay, the current model does not handle that, but the algorithm still works very well. Okay, I didn't show a quantitative value. They're actually their scores that we computed of the output reconstruction. I think the methodology itself is much more powerful than what we right now proved. I think it works for a much more general model with non-uniform distribution because the persistence simplification ultimately is not using absolute value. It's kind of using semi-relative difference to measure the importance of feature. So it's the relative. You can have in the low density area, you still have the road because compared to its neighbors, it's still much higher. Okay, so it's using, so in practice it works much better than what the theoretical results look. And this is just to show the three-dimensional example. Let me just, I think I'm running out of time really. Let me just stop here, just point out that this is, as I said, it's the very first step. And the algorithm methodology was for high-dimensional data, but especially after this morning's talk, I think it will be really interesting to think of a different way of thinking about this approximation. Can I get some sort of consistency reconstruction result that as your points sampled more and more, that you really converges to that ground truth and so on. Okay? All right, thank you for your attention.